Hi, this is part 2 of a lecture series on discovering polynomials. In the last Discovering Polynomials video, we talked about how to graph a polynomial function when it was given in expanded and factored form. We talked about how you could learn different things about the function based on information given with these two forms of the function. First, the end behavior can be found by looking at the leading coefficient. The y-intercept can be found by looking at the constant term, and the x-intercepts and their multiplicities can be found by looking at the factored form of the polynomial. With this information, it's pretty easy to graph at least a sketch of that polynomial function. In this case, we see that the end behavior is that it starts high and ends low. The y-intercept is at 12, and the multiplicities tell us the x-intercepts and whether the graph is going to bounce or go through the x-axis at that point. Once the polynomial is in factored form, then graphing a rough sketch is pretty easy. But what if the polynomial is not in factored form? For instance, what if we had f of x is equal to 4x to the fourth power plus 12x cubed minus 51x squared minus 58x minus 15? In this expanded form, we can tell some things about the polynomial. For instance, because the leading term has an even power and the coefficient is greater than 0, we can say that this graph opens up and up. And from the constant term, we can say that there is a y-intercept at negative 15, but we don't really know where the zeros are or the behaviors at those zeros. Our goal today is to take an example like this of a polynomial that is in expanded form and write it in factored form. So our goal is to talk about how to factor a polynomial function. To start us off, I want to talk about what we know about factoring quadratics. If we have this quadratic 3x squared minus 7x plus 4, and we wanted to factor that, we know that we are going to have two sets of parentheses. And we can think about what numbers need to go in the first set of blanks and what numbers need to go in the second set of blanks. For the first set, with the blue arrows, we know that when we multiply those two numbers, they have to multiply and give us 3x squared. So the only option here is to have 3x and x. That's the only way that we could get 3x squared, unless we used fractions, but we're not going to do that. For the next blank, that is for the ending terms, we know that those two numbers have to multiply and give us 4. In this case, we have several options. For instance, we could have 1 times 4 is 4, negative 1 times 4 is 4, 2 times 2 is 4, negative 4 times 1 is 4. There's lots of different possibilities for what numbers could go in here based on what multiplies to give us the number 4. In order to figure out which of these is correct, we have to then add the outside and the inside term to see if those equal to negative 7. However, the point is to think about all the different possibilities. If we looked at all the possible factors for the first term, 3x and x, and all the possible factors of the second term, which is 1, 2, and 4, this would be a list of all the possible factors that we could have in this case. So we have 3x plus 1, 3x minus 1, 3x plus 2, 3x minus 2, and so on and so forth. If this quadratic is going to factor nicely, it's going to be using these factors. If we want to think about the zeros or the x-intercepts that we would get from these factors, we can do so by simply setting each of these equal to 0. So for instance, 3x plus 1 is equal to 0. If we solve that for x, we would get negative 1/3. X plus 1 equals 0. If we set that equal to, or if we solve for x, we would get negative 1. In this case, we can factor this polynomial into 3x minus 4 and x minus 1, and the zeros we get are 4/3 and 1. We can also think about how the factors relate to the leading term and the constant term by expanding these polynomials. If we wanted to multiply and expand this polynomial, we would have to first multiply the first two terms, which would give us 2x squared minus 5x minus 3, and then we would have to multiply those two terms, which would finally give us 2x cubed plus 3x squared minus 23x minus 12. Notice that the leading terms, or the leading numbers in each of the terms, 2x and x, multiply to give us the leading term of that expanded form. Each of those original terms is a factor of 2x cubed. The same thing is true with the constant term. Negative 12 is found by multiplying 1 times negative 3 times 4, the constant terms of each of the linear factors. In this case, each of these is also a factor of negative 12. So it's actually quite easy to determine whether something is possibly a factor of a polynomial in expanded form. What we have to look at is each of the terms and ask whether they are factors of either the leading term or the constant term. So for instance, the first possibility here is x minus 1. Since x is a factor of 6x cubed and 1, or negative 1, is a factor of negative 30, then this is a possible factor. It may not be a factor of this, but it's a possible factor. The next example here, 5x plus 2, is not a possible factor. The reason it's not a possible factor is because 5x cannot go into 6x cubed. That is, that 5 is not a factor of 6. The next expression, 3x minus 5, is a possible factor. The reason that this is a possible factor is because 3x will go into 6x cubed. That is, 3 is a factor of 6. And 5 will go into 30. 5 is a factor of 30. This last example, x plus 4, does not work. The x does go into 6x cubed, but the 4 does not go into 30. 30 is not divisible by 4. We could ask the question in this way as well. Which of the following could be a root, or an x-intercept, or a zero of the polynomial? Notice that these zeros correspond to the factors above them. That is, if x minus 1 is a factor, then the 0, or the root, would be 1. If 5x plus 2 is a factor, then the root corresponding with that, or the 0, is negative 2/5. We get these by setting each of these factors equal to 0 and solving for x. So the only possible zeros that we have here that would work are the ones that correspond with factors that would work. So in this case, 1 is a possible 0, and 5/3 is a possible 0, because x minus 1 was a possible factor, and 3x minus 5 was a possible factor. Notice that the 3 on the bottom of the 5/3 corresponds with the 3x in that factor, and the 5 in 3x minus 5 corresponds with the 5 on top of 5/3. So now we come to what we call the rational root test. This will give us the ability to find all the possible rational factors of a polynomial in expanded form. If a 0 is a rational number, that is a fraction or a whole number, it must come from a factor of the form ax plus b, where a is a factor of q, the leading coefficient, and b is a factor of p, the constant term. So, by listing all the factors of p and all the factors of q, we can find all the possible rational roots by simply taking all the numbers p over all the possible numbers q. So in this case, we would take 1 over 1 and get 1, 3 over 1 and get plus or minus 3, 5 over 1 and get plus or minus 5, 15 over 1 and get plus or minus 15. Then we've exhausted all the numbers where the q value is 1, so we move on to 2. So the next numbers in the list are plus or minus 1 half, plus or minus 3 halves, plus or minus 5 halves, etc. In doing so, now we have a list of all the possible rational factors or rational roots. If a 0 is a rational number for this polynomial, it must come from this list. So that is the first step in factoring polynomials, knowing what are the possible factors. Now that we know what's possible, it's important to determine whether something actually is a factor of a polynomial. So in this case, let's consider the function 6x cubed plus x squared minus 47x minus 30. We want to determine whether x plus 3 is a factor of f. Well, if x plus 3 is a factor, then we know that negative 3 is a 0 of the function, or negative 3 would be an x-intercept. That tells us that if we evaluate the function at negative 3, that will equal to 0. So one thing we can do is simply plug in that number, negative 3, into the function. If we plug in negative 3 in for x and evaluate, in this case we get the number 42. Since 42 is not 0, then that tells us that x plus 3 is not a factor. Although it was an option based on the rational root test, it simply doesn't work. Another way to determine whether x plus 3 is a factor of f is by using a method that we call synthetic division. The way that synthetic division works is you put the 0 on the left-hand side in the box, and then you list the coefficients of the polynomial in expanded form, like so. Notice the coefficients are 6, 1, negative 47, and negative 30. In this case, we just forget about the variable part and just list the numbers. Synthetic division works like this. The first number we bring down for free. That is, whatever the leading coefficient is, it just comes down without having to do anything. Next, we multiply the number in the box by 6 and write it underneath the next number. So negative 3 times 6 is negative 18. Then we add those two values to give us the next number. Then we repeat the process. We multiply negative 3 times negative 17 to give us the number that goes under negative 47, which in this case is 51. Then we add those two numbers, which gives us 4. Finally, we multiply once again, negative 3 times 4, which gives us negative 12, and when we add that, we get negative 42. Synthetic division is actually very useful because from here, we can actually write the polynomial in a slightly factored way. Notice that if we wanted to factor 6x cubed plus x squared minus 47x minus 30 by x plus 3, that is if we wanted to factor x plus 3 out, we could do so, and what would be left is 6x squared minus 17x plus 4 with a remainder of negative 42. We can obtain this polynomial by looking at the numbers that we get in the bottom row of our synthetic division. The last number is always the remainder, which in this case is negative 42. From there, we count back adding a power of x every time. So 4 is now the constant term, 17 has x, and 6 has x squared. So this gives us that polynomial. Our goal is to find something that has a remainder of 0, because if you have a remainder of 0, that means that the number that you tried to factor it with is actually a factor. That is, it will actually be factored partially. You may have noticed that when we evaluated the function at -3, we got -42, and that the remainder when we use synthetic division with -3 was also -42. This is not just a coincidence. This is what we call the factor theorem. What it says is that if you evaluate a function at a number, that will equal to the remainder when using synthetic division with that same number. Sometimes it's easier to simply plug in a value to the function to see whether it equals 0. Sometimes it's easier to use synthetic division. I recommend using whichever method you think is easiest. So by using these techniques, we can factor polynomials. To determine whether a number, c, is a 0 or a factor of a polynomial, you can do one of two things. You can either plug the number into the polynomial. If it's equal to 0, then that means that x minus that number is a factor. Or you can use synthetic division, putting c in the box. If the remainder is 0 with synthetic division, then that means that x minus that number is a factor. So let's use synthetic division again to see whether x minus 3 is a factor of 6x cubed plus x squared minus 47x minus 30. In this case, we set up our synthetic division like this. 3 goes in the box, positive 3, that is, and then the coefficients, 6, 1, negative 47, and negative 30, go above. The 6 comes down for free. We multiply 3 times 6 and get 18. We add 1 and 18 to get 19. We multiply 3 and 19 to get 57. Adding negative 47 and 57, we get 10. Multiplying 3 times 10, we get 30. And here, we do get a remainder of 0. This is exactly what we want. This tells us that we can write 6x cubed plus x squared minus 47x minus 30 in factored, or at least partially factored form. That is, that x minus 3 is a factor, and that what's left over is 6x squared plus 19x plus 10. Now we have taken 6x cubed plus x squared minus 47x minus 30 and written it in partially factored form. Notice what we have left, the 6x squared plus 19x plus 10, is simply a quadratic, and so we can factor it using whatever method we want. In this case, it's easy enough to simply factor that into 3x plus 2 times 2x plus 5. So we've taken our original function that was in expanded form, 6x cubed plus x squared minus 47x minus 30, and written it in completely factored form, x minus 3 times 3x plus 2 times 2x plus 5. This will now allow us to graph the function. Let's look at this example from before. When we used the rational root test, we found that the possible rational roots were listed here. This gives us a list of things that we can try to see whether they are factors. This method requires a lot of guess and check. So let's start with 1. In this case, I think it's easiest to simply evaluate f of 1. That is simply to plug 1 into the function and see whether it equals 0. Well, in this case, we have 4 plus 12, which is 16, minus 50 minus 50 minus 15 or something. That's not equal to 0, so I know that x minus 1 is not a factor. Now let's try -1. I also think that just plugging this number in is actually easier than synthetic division. In this case, anytime you have an odd power, it will change the sign of the coefficient. So we have 4 minus 12 minus 51 plus 58 minus 15. In this case, this is also not equal to 0, and so therefore x plus 1 is not a factor. So what about 3? Is 3 a 0 of this polynomial? Well, plugging in 3 into this polynomial seems a little bit too complicated. We have to find 3 to the 4th power and then 3 cubed and multiply it by 12. It seems like it's going to be a lot of work. I think it'll be easier, in this case, to use synthetic division. So we take our coefficients, 4, 12, -51, -58, and -15, and then we put our 3 in the box. The 4 comes down for free. And going through the process of synthetic division, we see that in the end, the remainder is 0. So that tells us that x minus 3 is a factor. In this case, now we have partially factored f into x minus 3 times 4x cubed plus 24x squared plus 21x plus 5. So now we have partially factored f into two factors, but we need to see if we can factor the rest. That is, we need to get it into completely factored form. In order to do that, we can just concentrate on the part that's not factored. So using -5, let's see if that is a 0. If we go through synthetic division, we see that in the end, the remainder is 0, and that tells us that x plus 5 is also a factor. So we're almost there. In this case, we're down to a quadratic term that we can then use either factoring or the quadratic formula to find the remainder. In this case, we can simply factor 4x squared plus 4x plus 1 into 2x plus 1 times 2x plus 1. Notice that 2x plus 1 is a repeated factor. That is, it has multiplicity 2. So therefore, we can write it as f of x is equal to x minus 3 times x plus 5 times 2x plus 1 squared. So if we wanted to now graph this polynomial, we could now figure out these different aspects. We knew the end behavior and the y-intercept from before, but now we know that the zeros are 3, -5, and -1/2 with their multiplicities, and so we could sketch a rough graph of this function. In this discussion, we've talked about lots of techniques for factoring polynomials. The point is to factor them so that we can easily graph a rough sketch of that polynomial. The method goes like this. We first have to find the possible rational roots by using the rational root test. This will give us a list of numbers that we should try to see whether they're zeros. From that list, we have to guess and check by either plugging in those numbers into the function or using synthetic division. Once we determine something is a 0, then we can use synthetic division to get the function into partially factored form. We repeat the process until the function is in completely factored form. And once it's in that form, it's easy to graph. I hope this video can serve as a good introduction in how to factor polynomials. Thanks for watching.